So it's a great pleasure to be here. I'm George Danezis, and I'm usually teaching at University College London in London, also called UCL. So every time I say I'm from UCL, people always wonder if I'm from Leuven or something like that. It's apparently the famous one. So today I'm going to talk to you for an hour and a half about how we can do things that many of you, if you haven't heard of these techniques before, may think are just impossible, namely how to actually compute on data that we cannot see, that is encrypted. Okay? And it's a great pleasure to follow Bart Prunell's talk, who talked about the kind of basic cryptographic ideas, because here we're going to go into the realm of modern cryptography and a bit beyond what Bart said. And in fact, there will be mathematics. So if you have pen and paper, feel free to take it out. But we'll go very, very slowly. And hopefully, if you get into your memories from high school, we'll be able to get through them together without much pain. So let's first start by saying that, to some extent, all the material that Bart Prunell presented to you in the previous session is the easy part of cryptography, right? I mean, and he very correctly described the very classic problem where we have Alice and Bob, and this is Alice and this is Bob, and somehow they want to talk to each other privately, okay? So we have a number of solutions to do this. Bart Prunell went through some of them. We can assume that they share some key and then use some kind of cipher. Or we can assume that they don't actually even share a key, and then we use public key cryptography to establish a key and then use ciphers like the ones that Bart Prunell presented, and then they can talk confidentially. Now, this confidentiality hides the content, okay, but we assume that both Alice and Bob somehow collaborate in order to maintain the secrecy. There are some more subtle properties such as anonymity, where Alice and Bob wish to talk to each other without any third parties finding out that they're actually talking to each other, what the identities of the people talking are, or without even knowing that, without, for example, Alice knowing that Bob is sending messages to her. This is, again, if Alice, let's say, is a doctor and Bob is a bit embarrassed to ask for some information or other, he can basically send an anonymous email saying, hey, I have those symptoms. Is it, an embarrassing thing or not? Okay? Now, it turns out that for thousands of years, humans have studied this problem, and by now, in the last at least 30 years, we have pretty good solutions for doing this. Okay, so this is not what we will talk about today. Because consider now much more complex problems that have come up with the advent of modern information technology. For example, we have online communities, we have very complex interactions between different people online. Okay? So we want to do much more than just send messages to each other and talk to each other. We want to actually secure very complex processes. So let's take one very simple example, again involving confidentiality, but a very, very different nature than the one that can be covered through the secure channel that I showed you. In this case, we assume that Alice and Bob are millionaires. They're very rich, and this is actually the setting in which this problem was first set. And they sit around online and they wonder who's richer, okay? So Alice and Bob are sitting around wondering, we're both millionaires, but who is richer? However, they are a bit coy, they're a bit shy about telling each other exactly what their fortune is. They just want to know if Alice is richer than Bob or Bob is richer than Alice. Okay, so they clearly have some secrets each, right? They don't want to reveal what their fortune is, they just want to reveal one bit. This is known as the millionaire's problem. It's due to Yao, and it was presented in the 1980s to motivate this field. Okay? So now, the problem is here that both of them have secrets. They don't trust each other to tell the secret. However, they would like to get a function out, namely the kind of who's greater, which fortune is greater, from these two secrets without revealing anything more about it. And I hope that it is clear to all of you that this problem cannot actually be solved through the traditional secure channel that we have described so far in cryptography. It's not the problem that a third party shouldn't learn what they're talking about with each other. The problem is that they don't even want to reveal to each other some information, however they want to actually do something with it. Is that clear? Yeah? Cool. So this is, in fact, the first instance of the problem of computing on secret data. Okay, so in this particular case, what we can say is that Alice has a secret, and we will call these secrets X, so X of Alice, and Bob has a secret, and that is the secret X of Bob. And we want to compute a function f on these secrets and reveal the result y. Okay? However, we have some very specific security properties that we would like to hold. First of all, correctness. Indeed, we want to compute y, not some other function on these secrets. But the second and the most important for us here is privacy. Namely, after we have implemented a system like this, we would like both Alice and Bob to know the answer y, who's richest, without actually finding out anything else except for what y tells them about it, about the respective fortunes. Okay. And of course, this is a particular instance, but we would like to do this ideally for any function, right? We would like to, for example, in order not to use just silly toy examples, we would like to run an auction here for a particular good, let's say this pen, okay? And everybody here wants to actually put bids, and the result of the auction, this function f, is that, you know, the assignment, for example, it will say that the pen belongs to you, right? So in this case, again, we have this function f that should output who basically has bid for the highest amount, and they actually should be revealed, but nothing else about the actual bids that we have put in should actually be revealed, because that might reveal sensitive information about how much we value or not value the pen. Okay? So that's a second, much more realistic example of where we would like to use such private computations. Now, the usual way this is implemented in a strawman solution, a kind of simple, straightforward solution, is to somehow, for Alice and Bob to somehow find a trusted third party that they both trust with their secret, give that party the secrets, okay, namely their fortune in the case of the millionaire's problem, and say to that party, could you please tell us who is richest? Okay? So this is the kind of trusted third party solution. Now, and the trusted third party takes the inputs, produces the output, and hopefully needs to maintain the security properties. First of all, it computes the correct result. It doesn't lie and doesn't cheat. And secondly, and this is the difficult thing to achieve, it actually doesn't tell anyone else what the secrets were. Okay? And in fact, you have to trust this third party for both the confidentiality of the inputs, the integrity and the correctness of the output, and the availability. It should actually produce a result and give it to you. Okay, so that trusted third party is pretty trusted for all the properties we care about by both Alice and Bob at the same time. And there is, of course, a problem with these trusted third parties, is that, of course, they may not exist. Okay, they may not exist for many reasons, and these are always the 4 reasons you should keep in mind. First of all, it costs to run such a trusted third party. You know, who would be a trusted third party in the case of Alice and Bob trying to find out who's richest? You know, why would they do it? What's their business model for performing these operations for random strangers, right? I mean, maybe they will start charging, at which point is it really economically feasible to involve a third party that charges you for every, let's say, auction run or whatever? How do we implement it cheaply? In a way that we both can guarantee the security properties and the privacy properties, but also it's economically feasible to have it. So the cost is a big issue. Then, of course, there are the slightly more nefarious issues around this trusted third parties. The corruption is the first one. How do we know that this trusted third party indeed acts on your behalf and does not actually work with an adversary that wants to learn your secrets? Okay? And in fact, it's even worse than this, because even in the millionaire's problem, which is the simplest problem, we have both Alice and Bob that do not trust each other with their secrets. However, both have to trust the third party with the secret. So how do you know, if you, let's say, are Bob, that the trusted third party is not just more friendly with Alice than it is with you and will not reveal to Alice your secret? Okay, it's very difficult. It's a very fine line. Alice has to trust the third party, but not actually, the trusted third party should not actually be too close either and reveal secrets. Now, the third problem is compulsion with trusted third parties. So even if they are honest, someone may come with a gun to their hand and say, give me all the secrets that you know about. And then what would they do? Or a judge may actually come and say, look, you know, I'm a judge, I have legal authority to come and ask you for secrets, give them to me. And finally, they might get hacked. They might get compromised. Okay? So there are many reasons why cryptographers are very, very suspicious of solutions that are based on one entity knowing everybody's secrets, doing everything right, and then revealing the result and everything is fine. Okay? So this is not a very robust, from a security point of view, implementation strategy because of those 4 problems that I have illustrated. However, it is worthwhile keeping in mind this idea of a trusted third party that takes secret inputs in a function and produces the result, because really, if this party was to exist and to be trusted, this is really the specification of what we're trying to do. We're trying to solve that problem that could be solved in that way, but while removing all of these potential threats to our solution. Okay? Please, if you have any questions, just interrupt me and ask me in line, particularly later when we get a bit more formal. It's important not to lose the plot. So just ask me at any time. Now, so we would like, and this is the aim of this talk, we would like to do this computation on secrets without having a third party and without actually revealing the secrets to anyone else. And every time I start telling my students about this problem, they're like, well, that's clearly impossible. Okay, I mean, if you have to compute on some data, you need to see the data. It's a fact of nature, right? And if you cannot see the data because the data is secret, well, you clearly cannot compute on the data, right? I mean, it's obvious, it's self-evident to most people. And in fact, the whole aim of this talk is to convince you that not only it's impossible, but it is actually quite simple to do. And I will, in order to convince you, show you one particular scheme to at least do linear computation, sums and weighted sums, etc., and give you a hint about one more thing that you would need to make this system complete and be able to compute any function secretly on secret data. Okay? So that's the aim of this talk, to give you a taster of what it would take. Of course, Bart's warning applies. Don't just go home and start, a company that does it for money, unless you actually hire a few cryptographers that will take care of all the details. But in principle, you could actually use these techniques. Now, this is the most interesting theorem and the most important takeaway. You can, in fact, not only compute on secret data, you can compute any function privately without the need of a trusted third party. Okay, this is the most important result that we have in this body of work. Okay? You don't even need a coordinator. So in theory, if all of us just basically come up with secret bids for how much we would pay for this pen, we could just run a protocol amongst each other that decides whose bid is the highest, for example, okay? Without needing any trusted third party, without even needing a coordinator. Okay? And furthermore, our technique could be robust to cheating, some of us trying to manipulate things in order to get the wrong result, and also robust to denial of service attacks, namely someone just stopping replying to messages, hoping that the whole protocol will end. And not only we can do that for auctions, but we can do that for any function, okay, without revealing secret inputs. Now, there are 2 different adversary models under which we can do this private computations. The first one is when, let's say, all of us are honest. We would like to learn the secrets of everybody else, but we will actually follow the protocol steps correctly. We might at some point stop, but every protocol step we do is a correct protocol step. And then we could actually run these protocols if at least half of us plus 1 are honest. Okay? On the other side, if some of us are really, really dishonest and would be sending malformed messages around, then we can only secure those protocols if at least 2/3 plus 1 are honest here. And this has nothing to do with cryptography. It has to do with Byzantine failures and distributed systems problems to protect against some of us just going silent and never replying. Okay, so in practice, both honest but curious and Byzantine failures can be tolerated quite efficiently, and the protocols to do that are not a problem. It is unlikely you're in a posse of people, all of them or 2/3 of them being dishonest. Okay. Now, one quick insight first. I said something very powerful here. I said we can compute any function, okay? And this is quite a profound result, right? And you'd be wondering, how does one go about showing that you can basically compute pretty much any function secretly? You know, what kind of ingredients do we need in order to even show that? Because that will also lead us to conclude what we would need in order to compute any function. So the idea is the following. If we look back at computation theory, and you know, your basic electronics, etc., you may remember that there is one special electronic gate called the NAND gate. Okay, and the NAND gate is like AND. Okay, so in normal AND, if you have 0 and 0, you have 0, 0 and 1, you have 0, 1 and 0, you have 0, and 1 and 1, you have 1. That's the normal AND gate. The NAND gate just negates the result. So now for 0, 0, whereas you would have 0, you have 1. For 0, 1, you would have 1, 1, 0, you have 1, and 1, 1, you have 0 instead of 1. Okay? Now the NAND gate is actually quite special in that it is what we call a universal gate. Using NAND gates, you can build any other logic gates. And therefore, using NAND gates, you can build any combinatorial logic circuit. Okay, and if you can build any combinatorial logic circuit, you can basically build any function of up to a certain depth. Okay? So you cannot have arbitrarily recursive functions that never basically finish, but these are not actually that interesting for us because we want actually our computations to finish and converge. So that's not a big deal. Practical functions can all be expressed as in terms of NAND gates that are connected in different ways with each other. Okay? So far so good? Now, it turns out that we can express a NAND gate, namely this truth table there for this function, using simple arithmetic. Assuming that the inputs are either 0 or 1, like they are there, you can convince yourself by solving the 4 cases that this output Q can be interpreted as 1 minus A times B. Okay, we can do it together if you want. Look, 0 and 0. That becomes 0, therefore we have 1. Great. 1 and 0, that becomes 0, we have 1. The other way is the same. And 1 and 1 becomes 1 minus 1, 0. Hey, it works. Okay, simple arithmetic so far. The maths is not too taxing so far. I hope you're okay. So, what does that mean? It means that, and this is the important thing for us here, it means that if we can do multiplication of 2 bits, and if we can do addition, which subtraction is a form of addition, the addition of the inverse, then we can actually model an AND gate, okay? And then we can compute any combinatorial circuit that then allows us to compute all interesting functions, okay? So now let's go back into how do we prove we can actually build, let's say, a universal scheme that would compute any function on secret inputs. Imagine the following. Imagine if we could express binary digits, A and B in this case, as secrets, okay? As secrets. So we now have an A and a B, but we don't know exactly what it is. And imagine we could just do addition on these secrets and multiplication on these secrets. And note that these secrets are just binary digits. They're just secrets of either a 0 or a 1. Okay, but we don't know which by actually looking at it. Okay? Then what we could do is we could actually compute these just on secrets, hopefully get as a result of this computation another secret representing the output of the NAND gate, and then chain these together to represent any computation on secrets with secret inputs, secret outputs, secret inputs, secret outputs until we actually get the result. Okay? So basically, what we're missing as ingredients in order to be able to compute any functions on secrets is a way of expressing binary digits as secrets, a way of combining those secrets to do addition and multiplication, assuming that they're just binary secrets, and a way to actually make sure that the result is itself a secret and can be carried forward to do further computations. Is that cool so far? Okay. And in fact, what we're going to do here for the next hour or so is I will show you a way of expressing, in fact, I will argue there are two different ways, but I will show you in depth a way of expressing binary digits as secrets first. I will show you a way of doing addition. I will tell you and argue that there are ways of doing multiplication privately, and there are slightly more complex schemes that allow you to do multiplication. However, we will not actually go into the multiplication, and I will show you that the whole thing just adds up, and you can continue doing all these computations. Okay? This is what we're going to focus on. How do we represent digits? How do we do addition between these secrets, which you can use as well to do other computations that are interesting, and then I hope that after that I'll convince you that doing multiplication is kind of similar to that. Okay. So I mentioned that we will look at one approach in depth, but there are two approaches that you should be aware of every time you think, can I compute on some secrets? The first one uses encryption. Okay? However, these encryption schemes are quite special. They're not quite like AES that we have seen before, or like DES or anything like that, because AES and DES, if you encrypt a 0 or a 1, okay, then you cannot actually do any operations on them. So you cannot do addition or multiplication on them, therefore you cannot compute secretly on them. Okay? So DES, for example, or AES as a cipher will not do to allow you to do computations here. So what we need to do is we need to express 0 and 1 as encryptions, but then we need to actually have a special encryption scheme that allows us to do operations like addition and multiplication on the ciphertext. So I will show you how to build that scheme here. There is another scheme that allows us to, again, express bits and do operations on them that does not involve encryption. It is called secret sharing. The idea is that we again want to perform an operation altogether here with secret inputs from each of us. Okay, like before, like let's take the auction example where we each have a bid for this red pen that is magnificent. Okay? But instead of encrypting our bid, like in the homomorphic encryption case, which we will see in detail, what we do is we split the secret into many shares, let's say as many shares as there are people in here, and we give a share to each of us. Okay? So everybody basically splits their secret and then distributes it around. So now each of us holds a share of the secret of everybody else. And of course the assumption is that we're not all going to cooperate and collude in order to reveal any one particular person's secret. Okay? And then using those shares we can actually implement addition and multiplication using online protocols, allowing us to do secret computations. I will show you some pictures and some discussion about this, but I will not actually go into detail about how we use secret sharing to do this. That's probably for another time. Okay, so now let's go in depth a little bit in the first scheme, how to use a homomorphic encryption scheme, namely an encryption scheme that allows us to do some operations on secret data to allow us to do private computations. So let's first look at the big picture here. As for encryption, we have Alice and Bob, but now they try to do something very different than talk to each other. So as we said, in the homomorphic encryption scheme, what Alice and Bob do is they encrypt their secrets using a special encryption scheme. Okay, so Bob encrypts his secret x1, Alice encrypts her secret x2. And then they just publish those. They can tell the world. They're encrypted, therefore it's not a problem. Under which key, we will see. Okay, but assume the adversary doesn't have the key, otherwise everything is lost. They publish these things, and then anyone pretty much can actually do additions and multiplications on these secrets. And we will see here how to do addition. And then what comes out of basically this operation on secrets, on ciphertexts, not on plain texts anymore, okay, is actually a ciphertext of the result. Now, there was a lot of hype maybe a couple of years ago around the idea of fully homomorphic encryption that allows you to indeed do both additions and multiplications on secret in order to support such scenarios. And I heard a lot of basically nonsense about how you would be able to somehow give the clouds your private data, and then the clouds, and here we have a cloud basically to illustrate that, would do operations on this private data, and somehow the answer to some joint computation would pop out, namely the actual answer, y, not the encryption to the y. Well, that is not something we know how to do, actually. Okay, so the result of homomorphically operating on ciphertext generates ciphertext, not plain text. Huh? And somehow, when we will see this is not trivial, we will have to then take the ciphertext representing the result and decrypt it in order to actually get to the result, namely who won the auction or who's richest or whatever. Okay? So that's an important consideration here. So now let me show you a simple is of course relative. We will go slowly, but it is one of the simplest, sadly, that we have. Additively homomorphic encryption scheme. This is an encryption scheme that allows you to generate some keys, and it's a public key scheme, so it has a public key and a private key that only one person knows. It allows you to encrypt zeros and ones, or actually any other number of values that you wish. It allows you, of course, to decrypt them, otherwise it would be pretty useless. But it also has more properties than that, because so far AES or any other encryption scheme might also have them. It allows you to take ciphertexts and add them. By add them, I mean you take the ciphertext, you do an operation on them, and what you end up with is the ciphertext of the sum of the other two plain texts that you just added. Okay? Sadly, I will not show you one that has multiplication, because that would take about a day rather than an hour. But I will actually point you to the places where you can find those. Now, there is something really interesting here, which is that when I say multiplication, what I mean here is multiplication of two secrets. If you can do addition, you can actually do multiplication with a public constant without a problem, because multiplication with a public constant is just applying addition a certain amount of public amount of time. So we can actually do multiplication with a constant. We cannot actually do multiplication of secrets with each other, because we don't know how many times to add one secret to itself if the other number is secret. Is that cool? Yeah? Okay. So let's start with some very basic assumptions. In modern cryptography, we try to reduce the security of more complex ciphers to simple mathematical problems that mathematicians are studying and are believed to be hard to solve. Now, the most interesting such problem that leads, in my opinion, to some of the most practical schemes, cryptographic schemes out there, is what is known as the difficulty of taking the logarithm in some groups. Now, discrete logarithm problem. Now, what is the idea here? The idea is that somehow, imagine we have a number g, and I use number here loosely, an element g. This is just, you can think of it as a very big number from 0 to a very big prime of 2,000 bits or so. But it's ultimately, you can think of it as just a number. And then we take another number x, which is again a very big number from 0 to some thousands of bits at random. It is easy and efficient relatively to compute g to the x. Okay? We just multiply g x times with each other. In fact, we don't do this quite so naively. There are very fast algorithms for doing so. So far, so good. Given g to the x, we multiply g x times with itself. We have g to the x. That's quick and easy. However, it turns out that doing the opposite is actually extremely hard. So what is the opposite? If I give you the same g that I gave you before, and now I give you g to the x, okay, this result before, it is difficult to find x. What does that mean? It is difficult to find how many times to multiply g with itself to get any other arbitrary number. Okay? And this is normally would be just a logarithm if we were working with reals or something like that. But because we're not working with reals, and where these g's are in fact doing all their mathematics in modular form, like a clock arithmetic that goes round and round and round and round, it is difficult to actually tell how many times we've gone round, etc. And therefore it is confusing and quite difficult to compute what this x is. So one way is easy, the other way is hard, and that's a mathematical assumption we're making. Maybe tomorrow some genius is going to find a way of solving this. In fact, this is the problem that quantum computers solve, hopefully, if they ever work. Okay? And then we will have to just throw away everything I told you and find a different assumption on which to base our mathematical schemes and our cryptographic schemes, which is pretty scary. Thankfully, we have some other assumptions that don't suffer altogether in the same way. Now, as I mentioned, you can think of these operations here as being just mathematics on a big clock, in the same way as when we were children, we were learning how to do mathematics on our clock from 0 to 11, then 11 plus 1 is back to 0, and 11 o'clock plus 2 hours is 1 o'clock. That's just clock arithmetic. It goes round and round. Okay? Basically, all arithmetic we're doing in these fields is, again, modulo a very big clock that has as many little notches as a big prime. And when I say big, I mean 1024-bit big prime. Okay? So you can think of it in that way, if it helps you. It's just arithmetic in a big clock. Okay? Or, if you actually want very fast and very efficient implementations, you don't anymore use big numbers and arithmetic on a big clock. You instead use points on elliptic curves that turn out to be defined in such a way that we can actually do arithmetic between them. We're not going to cover that anymore, but everything I say here can be done in a very compact and efficient way using these elliptic curves. So let me introduce you to the Benalo cryptosystem. Josh Benalo is a famous cryptographer. He was my colleague at Microsoft Research when I was working there. And he was one of the pioneers of electronic elections. In fact, he started discussing about the possibility to do elections online, purely online, back in the early 90s, before most people had even heard of the internet. Of course, electronic elections are a very controversial topic these days. It's not really clear we can solve problems of coercion. If you're behind your terminal at home, maybe you have someone with a gun to your head forcing you to vote in some way or another. So there are actually some considerable security problems in fielding electronic elections. However, Josh basically looked very deeply at the cryptography of how we could manage these election systems quite early on. And it is in this context that he proposed this additively homomorphic encryption scheme in order to facilitate election systems. And we will see in a second an example where we can use it as such. Okay? And this is a slight modification of his cryptosystem to make it more efficient for some reasons here. So the first thing that a cryptosystem has to do is generate keys. Okay? Now, if you use a block cipher, it's just any random string of 128 bits. Public key cryptosystems are a little bit more fragile about these things. So let's see how we generate keys first. So first of all, we assume that there are some public values that everybody knows about the cryptosystem. They're not secrets. They don't have to be regenerated by anyone. They're just G and H, which you can think of as two big numbers that are public. There's nothing that special about them, except that you shouldn't know the discrete logarithm of the one versus the other. So if you just pick them at random or hash something to get them, you're good to go. And then key generation works as follows. Whoever is to hold the secret key generates a random number x, big number again, and the private key is just x. That's it. Okay? And then the public key is g to the x. So g multiplied itself x times. Okay. Now, because of the security assumption that we talked about in the previous slide, I hope you are convinced that if I give you the public key, g to the x, okay, you will not be able to find my x because of the hardness of solving the discrete logarithm problem. Okay? So the idea is that we have some entity that has the x, and everybody else has the g to the x, and that's the public key. Good. Now, the second algorithm, which we should have, is encryption. Okay? Now, encryption in this Benalo cryptosystem works by taking a message and also generating a random nonce, combining them and getting a ciphertext. And what is interesting here is that ciphertexts are not just one big string, but two elements, two numbers, effectively. Okay? And I hope this doesn't pose you any conceptual problems, the fact that instead of having just one bit string, we actually have two numbers, and that's a ciphertext. It hides perfectly well what the message is. So the idea is that I want to take the encryption of M, under some public key, of course. We always encrypt under a public key. So what I do is I find out a random K, and I will always denote the random K here, even though it's not actually an input of the encryption algorithm, just because I would like to illustrate to you later how these random Ks change. And then what I do is the following. I raise G. This is a public value G, as we said before. Everybody knows it, to the K. So I multiply GK times with itself. Now again, because of the hardness of the discrete logarithm problem, I hope you're convinced that G to the K does not leak K. Okay, because that's hard. We've said that before. And then the other thing I did is, on the second part, so far I haven't used the message yet. This can't possibly be it. Then I take basically my public key and I multiply it with itself K times. Okay? And then I multiply the second number that is public H M times into this. So I have H to the M. Okay? Now the insight here is that because of the difficulties associated with discrete logarithm problems and all that stuff, if I take the public key to the K, this is indistinguishable to an adversary from just a random element. Okay? And that totally hides the information in the H to the M here. Okay? So an adversary that is not able to somehow distinguish this from a random element is not able to tell anything about H to the M. Okay? And there is a kind of more formal way of showing that the adversary cannot actually distinguish anything from that except if they have the secret key. I will not go through here now. Now, to you at this point, it should be a little bit mysterious why this is the form of the encryption. Okay? Why? Okay? Why? That's it. So let's first of all convince ourselves we can decrypt it. Okay? And then let's actually look at how we can do operations which will justify why it is in that form. Okay? Otherwise, it's just weird symbols there. So first of all, I would like to convince you that we can decrypt this thing. Okay? So the decryption works by taking a ciphertext, and I will call the first element of the ciphertext A and the second element B. Okay? So we have two parts to the ciphertext, A and B. The first one is G to the K. The other one is public to the K, H to the M. Okay? And I would like to decrypt it with a secret X. Remember, in a public key encryption scheme, the decryption requires the secret key. Okay? So X has to play some role here, otherwise we've done something very, very wrong. Very wrong indeed. So the way to do the decryption is simply to take the second part of the ciphertext B, okay, and then divide it, okay, with A raised to the X. So A multiplied X times with itself. Now, why does that work? Okay, why does that work? So what happens is that B is G to the X, because that's the public key to the K, times H to the M. Okay? So that's basically substituting the public key into the second part of the ciphertext. And then when I divide it basically by A to the X, I divide it by G to the K, which was A, to the X. Okay? But look, this and that are exactly the same. And when I divide, they cancel out, and I end up with H to the M. Okay? Now, H to the M contains my message, okay? But it doesn't quite directly contain my message, because it's just this H constant that everybody knows multiplied M times with itself. And now, if you've been paying attention at our security assumption, you will tell me, well, that's no good. That's really not good. Because to extract M, I need to take a discrete logarithm again. You know, finding M is answering the question, how many times do I multiply H with itself to get that value here? And that should be hard, right? That should be hard. I shouldn't be able to do that. However, in this case I am. Why is that? Because as we said earlier, we do not really care about having very large values of M. In fact, in order to do computations on secrets, we only need to be able to encrypt two values, 0 and 1. So it is actually easy to find out if this H to the M is containing a 0 or a 1, because I can just compute H to the 0 and then compute H to the 1, okay, and compare which one it is. Okay, so I just brute force the decryption, because it's not much of a brute force, it's just a handful of values that I care about. Is that clear? Yeah? Okay. Now, another thing that is very important to realize, and I will go back one slide just to illustrate this again, is that, as I mentioned just now, what we really care about here is encrypting zeros and ones. But of course, if the encryption of 0 was always the same and the encryption of 1 was always the same, then that wouldn't really provide much protection. Okay? Because the adversary would be able to look, let's say, at a circuit that I do a computation on, that in theory is all encrypted, but then it would see which values are the same, and it would know that all of these, are the same, either all of them 0 or all of them 1. Okay? So it is absolutely imperative that an encryption of a 0 from another encryption of 0 look different to the adversary. This is very important. And this is exactly why we use this random k here. Because you see, this random k makes every encryption different, no matter what is being encrypted. Okay? So g to the k is always different for a different k. And even public key to the k is always different, even if the m is the same. Therefore, when I see two ciphertexts, I am not able to tell if their encryptions are 0 or 1, or even if they are the same, both of them encryptions of 1 or both of them encryptions of 0. And this is absolutely crucial in order to do this kind of computations. Okay, any questions so far? Don't be shy, don't be shy. Okay, so what we have seen so far is, how do we generate keys? X, G to the X, done. How do we do encryption? G to the K, public to the K times H to the message, done. How do we decrypt? B divided by A to the X, done. Okay, so far, this scheme is basically like the traditional El-Gamal scheme that some of you may have heard of. Now, this is the magic. This is why we care about this scheme. Now, I promise to you that I will show you how do we take two ciphertexts without knowing the key, the secret key. Okay, I'm not talking here about decrypting those ciphertexts and doing something. Just the ciphertext without being able to decrypt them, and then compute somehow on them. Okay, and in particular, what I would like to compute to start with is the sum of their plaintexts. These ciphertexts represent some plaintext for someone who would know the key. You don't know the key, so you don't know what the plaintexts are. Tough. However, just from the ciphertexts, you want to actually compute an encryption of the plaintexts they would represent. And how do I do that? So let's first write out what my ciphertexts are. Imagine we have a ciphertext of message 0 and do some randomness k0, which we don't care very much what it is. And we represent that as A0, B0. Remember, our ciphertexts are two elements. By convention, I call the first part A and the second part B. And then we have a ciphertext of message 1, okay, under another randomness. And then again, we represent that as A1 and B1. And what it turns out is that if I take the ciphertext element-wise and I multiply them with each other, okay, so I multiply the A's together and I multiply the B's together, then what I end up with is a ciphertext of the sum of the messages. And of course, also the sum of the randomness that I use, but we don't really care about that all that much. It just works out. And at this point, you're like, whoa, why does that work at all? Okay, what went on here? And what I would point out is that if we multiply g to the k0 and g to the k1, we just end up with g to the k0 plus k1. So we just have basically a new random value, okay, which is k0 and k1 here. No big deal, but it's still g to the k prime, okay, something else, which happens to be k0 plus k1. So the first element seems to be okay-ish, but now we need to make sure that the second part kind of also pans out okay. Now, if I take the product of b0 and b1 here, what I end up is having this ugly thing, but this ugly thing really is not that scary. It turns out that h to the m0 and h to the m1 just become h to the m0 plus m1. Now that is cool, because remember, my encryption is h to the message, and here we have h to the message 0 and message 1, which is exactly what I want. I want an encryption of the sum of the messages. Okay, so that's good. That's pretty good. And then if we actually gather the G's together, it turns out that these two G's are just public key to the K0 plus K1, which is again the same as my K prime. Therefore, if you remember what our encryption was, which is G to some K, public key to some K, H to the message I want to encrypt, it pans out that if I multiply those two together, it ends up being G to some K, public key to the same some K, H to the sum of the messages, and we're good to go. We're good to go, right? So I used two secret stuff, two ciphertexts. I don't know the key to decrypt them. I did some magic operations with them, which are not actually quite so magic. It's just multiplication. It's not the end of the world. We can do that, okay? And now I've ended up with a ciphertext of their sum. And I still don't know what either my inputs were or my output is. I just know that it's their sum, okay? So I hope I have convinced you that, yeah, if you build your cryptosystem with a little bit more care and with some properties that you want to achieve in mind, you can actually build cryptosystems that hide most information but allow some what we call malleability, some operations to take place on the ciphertext. And this is the key example. Now, I said to you already that multiplications of two secrets with each other is not something that this cryptosystem can do. However, we can do something else that is quite interesting, which is multiplication by a public constant. Okay? And this is how we do it. Imagine we have a public constant C, and then we have an encrypted message, M0, K0, that is represented as A0, B0. Again, two elements of the ciphertext. So how do we achieve multiplication? We basically take each of these A0 and B0, and we multiply it with itself C times. So we raise it to the power of C. Okay? And that, again, leads to the encryption of C times the message. So I have managed to multiply now the plain text inside this ciphertext by C without knowing the secret. How does that work? Again, we just have to basically write out what the A0s and B0s are. So G to the C K0 is just a new K prime. So now my K prime is C to the K0, no big deal. That's fine. And then if I raise the B0 to the C, we end up with public to the C K0, which is the same as my K prime. That's cool. And then H C times M, which is a multiplication of my message by C, which is pretty cool, again, so it works out. Now note that I can only do this in public without knowing the secret because C is public. If C was itself a ciphertext, I wouldn't actually be able to do this at all. Okay? Very important. Okay, so this is all the maths. We can relax a bit. Okay, and the slides are going to be available, so feel free to spend your evenings, writing these things on napkins and convincing yourself that every step actually works. Okay, I'm not lying to you. However, let's just look at now that you're convinced that at least it is possible at all, even if all the details are a bit fuzzy, how do we actually use these schemes? Let's take a very simple example. So imagine we want to do a simple poll, and this is in honor to Josh, who proposed this cryptosystem. Let's take a simple opinion poll. Do you prefer the color blue, or do you prefer the color red? However, you're a bit embarrassed about which color you prefer, and you would rather basically your input about whether you prefer red or blue being secret. Okay? So how would we actually use this scheme to achieve that? What we would do is the following. Each of us would submit two ciphertexts, one for blue, one for red. Okay? And then if we like blue, we would submit the ciphertext of 1 for our ciphertext for the blue, and of 0 for the ciphertext of red. However, if we prefer red, we would do it the other way around. We would vote with 1 for the ciphertext of red, and with 0 for the ciphertext of blue. Now, because both of these are ciphertexts, when we publish these two votes, one for blue, one for red, none of us here who doesn't know the key would be able to tell what we voted for. We would see a ciphertext and a ciphertext, nothing more. However, all of us, or some cloud in the sky, as you prefer, would be able to take the ciphertext and then add up the votes for blue and add up the votes for red and come up basically with the sum of votes for blue and the sum of votes for red. Yes? And now we would end up with the ciphertexts for the sum of the blue votes and the sum of the red votes. And this is what it would look like in case you prefer pictures. So this is Alice. She votes for the second thing. Let's call it blue and red. So she votes for red here. Okay, so she has 0 for blue, 1 for red. This is Bob. Bob prefers blue, so he votes 1 for blue and 0 for red. And let's imagine there are many, many more people. And then at the end, all these ciphertexts here, we use exactly the properties of addition that we have looked at. We add them up using the homomorphic addition, and we end up basically with ciphertext of the tally. And as we can see, blue is twice as popular as red. However, it is impossible to tell, because all of these things are ciphertexts, who prefers blue and who prefers red. Okay, now silly example, but that's how it is used. But there is a problem with this now. Okay, first of all, the problem is that the sum is not anymore just 0 or 1. So when it comes to doing this decryption, we have to do a little bit more effort to create a table that is big enough to be able to decrypt all values without having to solve a discrete log problem. So that's not actually such a big deal. The big deal is that I have pushed under the rug the question of who holds the private key. So I have merrily told you that, oh yeah, you know, Alice encrypts under some public key her votes, and Bob also encrypts under a public key his votes. And of course, that public key has to be the same for everybody, otherwise we can't do the homomorphic operations. But whose key is that, right? Who has generated that key? And this is like an important question, because whoever knows the secret behind that key, and remember, a public key is just g to the x, therefore there is an x secret that could be known by someone. Whoever knows that x can actually decrypt all the votes. Okay, it's like this magic golden key that just unlocks all privacy. Now, it is obvious to you, I hope, that if that entity is just a single entity, it's me, or it's you, or someone else in here, well, that is basically like a trusted third party. Okay, instead of doing all this little dance, okay, with ciphertext and adding them and all that stuff, we might as well just tell them our secrets. Since we trust them not to use their private key to open the ciphertext, we also probably trust them to just, you know, hear our secrets and not tell anyone. Okay, and they can do the computation and they can tell us the result. So it's a really bad idea for this private key to be in the hands of one entity. Okay, I hope that's problem. Otherwise, the scheme is useless. Okay, so thankfully, it is not necessary to actually have a single entity that holds that key. And this is possible because the same scheme that we have described in the previous slides can be slightly modified to do what we called threshold decryption. What is the idea of threshold decryption? The idea is as follows. Instead of actually having one entity doing key generation, we have many entities. Potentially all of us in this room, we can do our key generation. And then we can aggregate all our keys to make one big public key for the whole group. Now, the idea of this one public key for the whole group is that each of us now has to cooperate and collaborate with the decryption of a ciphertext. Therefore, it is impossible for a single entity to just decrypt everything, because all of us would have to actually cooperate. And of course, in practical deployments, you can choose how many entities you wish to involve to make sure that not all of them are corrupt and actually decrypt things behind each other's back. Okay? Now, I lied to you that this was the last maths. There is in fact more maths. So, how does threshold decryption work in the Benelux cryptosystem or the modification? The idea is that we are now all running key generation, so we all have a secret key X each, okay? And then what we do is the public key is G2 the sum of all our X secret keys. Now, how can we compute that? What we can do is we can basically each publish our own public key and multiply them all together, and that ends up being the public key for the whole group. That's pretty cool. Now, decryption, though, requires all of us to play along. So instead of just being b divided by a to the x, because there is no single x, we actually have to each take the b and then divide out our own shares of the key. Okay, and divide and divide and divide. And that will lead to the h to the m, actually, that we had before. And why does that work? It works because if you take bit divided by a to the x1 and you divide that by a to the x2, blah, 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 you end up with b divided by the a to the x1 plus xn, and therefore that is the same as the secret that was used as part of the public key, and that ends up decrypting the whole thing. So what can we achieve here? What have we achieved here? We have taken a scheme that potentially would have a single entity having a decryption key that would act as a trusted third party and could actually violate everybody's security properties. And we have turned it now into a scheme that allows us to do encryption, decryption, homomorphic addition, to do this fun poll that we did together, and doesn't have a single entity, because now when we get those ciphertexts as results here, we don't just have one entity that can decrypt them, but then we have to run this distributed decryption amongst everybody in this room to be able to extract that this is 10 and this is 5. And if any of us is actually honest, no one can learn anything about those values here. Okay? So this is a simple mechanism to do addition. Now, as I said, in order to have a complete scheme, we're missing multiplication. But don't be fooled, because a lot of very high value computations are actually linear computations. And I'll just give you one example of a practical system that I have designed myself. In the UK, there was a large smart meter deployment. And the idea was that smart meters issue how much electricity you have consumed every half hour. And somehow you want to know how much the bill is going to be. And the bill is determined by the amount you consumed at a particular half hour times the tariff at that time, which is public, summed up. Okay? So you can see that this is just a linear computation. Okay? It is how much you have consumed in terms of electricity times a public tariff, all summed up together. Okay? This is exactly using the operations we have seen here. So in theory, and in fact, we propose systems that allow us to do this computation on ciphertext, and the idea there was that the meters basically output, instead of readings, they output ciphertexts. Then you provide this ciphertext to your electricity company. Then they can compute a bill that is encrypted and just decrypt how much you owe them, so that they don't know how much electricity you consume every 5 or 10 or 15 or 20 or 30 minutes in your own home. Therefore, they cannot find out what your lifestyle is, what your religion is, etc. So even this very simple scheme here can be used for polling, can be used for billing, can be used for all sorts of things, even without having the ability to multiply secrets with each other. Okay. Now, of course, even though you can express high-value computations, it is nice to be able to multiply secrets and then be able to execute arbitrary circuits. Okay. Now, there are a number of other crypto systems that offer homomorphisms. However, they all have drawbacks. And this is actually why I'm not presenting them to you here. So if you take the traditional RSA, the kind of school RSA scheme, it also has a homomorphism. If you take two RSA ciphertexts and you multiply them with each other, you end up basically with the ciphertext of the product of the plaintexts. So it's a multiplicative homomorphism. Okay, so if you only want to do multiplication of secrets and no addition, then you can use RSA. Okay? But there is no addition. That's a problem. So the Palier crypto system, invented by Pascal Palier, has an additive homomorphism, a little bit like the variant of Benalo I have proposed to you. And in fact, you can encode very large ciphertext. So it doesn't have the restriction that very large plaintext. So it doesn't have the restriction that the plaintext has to be very small, 0, 1, or up to a small integer. So that is very popular. However, you can't do multiplication straightforwardly. Okay? Then there are schemes based on pairings on elliptic curves. These are like magic unicorns that allow you to do one multiplication between secrets, just one. But then the result of this one multiplication is no more a valid ciphertext in your scheme. Therefore, you can just now add it or decrypt it and you're done. Okay, so one multiplication per pair of secrets. That's not so good. And then in 2009, which is recently in my books, Craig Gentry came up with the very, very first fully homomorphic scheme that allows us to take ciphertexts and do both addition and multiplication on them. Okay, so this is actually quite a recent invention. Before that, all was not lost because you could still do multiplication using an interactive protocol. Okay, so you could actually do a little protocol to do multiplication, but you couldn't just give all the data to a cloud, let it do computation, and get it back. Now, Gentry scheme is a breakthrough cryptographically and scientifically. There is no question about that. However, it is not something you would ever want to use. The public keys are gigabytes long. The ciphertexts are gigabytes long. Doing one computation takes minutes, many minutes, for one bit. So it's not actually something that you want to use for doing computations at all. However, once Craig came up with that scheme, many people realized that, hey, I don't need to do any number of multiplications. I don't want to express computations that have potentially an infinite number of gates, one after the other. Most of my practical computations have a very limited depth. Okay? This is why we have chips that work at all. Otherwise, we would have to have infinitely large circuits. So lots of people started concentrating on a related problem which is the somewhat homomorphic encryption. So somewhat homomorphic encryption allows you to take ciphertext and do a certain amount of multiplications on them, not infinite, but more than one, in such a way that in a tunable way you can basically determine how many multiplications your computation needs to do, define a somewhat homomorphic encryption scheme using a tunable parameter that allows you to do that number, and then running with it. And these are actually practical. Now, practical means their public keys and ciphertext are a few kilobytes. However, the operations are very fast. Addition is super fast, and multiplication is also a few milliseconds. It's not actually that long. Okay? So that's pretty cool, because now we can actually do, for specific functions, we can instantiate a scheme and do computations on that functions on secrets. So that's really what you should be using if you want something general in the space of homomorphic encryption, not the fully homomorphic encryption stuff, which is too powerful probably for what you need. Okay, so what is so cool about homomorphic schemes before we move to another topic? So I hope you agree with me that the architecture is actually quite elegant and simple. We all take our own secrets, we encrypt them, we give them to the cloud. The cloud can actually do computations on these secrets and end up with ciphertext with the answers. Fine, good. Everybody can, in fact. Okay? And then we just run some threshold decryption, if it is a public, if the result is a function that we all should learn, and get back the result. Okay, so it's a very simple pipeline. It starts with people with secrets encrypting, then they're not involved anymore in anything. All the magic happens in big data centers. Those data centers can be insecure if you want, right? Because they don't handle secrets anymore directly. They handle ciphertext. And then you actually go through an end of the pipeline to do the decryption, which again has to be secure because it does handle keys. Now the nice thing is that the computation that is done on the ciphertext can in part be secret as well. The cloud doesn't have to reveal potentially some parameters of the computation. So let's take the example of genomic testing. Okay? The idea is that you're a pharmaceutical company. I am someone who's worried about having a genetic disease. You spend a few billion coming up with some test, okay, on testing my genome to find out if it has a disease. You don't want to tell me what the test is because I will steal it and then start selling it to other people. I don't want to tell you what my genetic data is. So what can we do using this idea? I basically encrypt it using a homomorphic scheme. I give it to you. You use your secrets on the encrypted stuff that I gave you to do the computation. I don't have to even see the computation. You return to me a ciphertext of my result. I decrypt it. I find out how susceptible I am to the disease. So that's also a very concrete protocol that we have proposed based on these ideas. So it's actually quite nice that we can have, to some extent, part of the functions being executed in the clouds being secret as well. Okay. However, it also has some disadvantages. And the disadvantage is that expressing general computations as circuits is cumbersome. Okay? In particular, you cannot do anything like binary search, or you cannot have indexes and look into indexes, which make operations log n in the size of the index. You instead have to execute the whole circuit, which is always the size of your circuit. So in terms of efficiency, we lose a lot by using these schemes. And of course, again, in terms of efficiency, we have taken every bit of the computation in the general case and turned it into 160 bits in the case of elliptic curves, 1024 bits in case we use integers, or 30 kilobytes in case we use one of these somehow homomorphic schemes. So we have a blow up here of many orders of magnitudes on the amount of data we're handling. Okay, so the idea, and again, I have seen that kind of nonsense hype a few years ago, the idea that you will take your enterprise application and instead of running it on a data center in the clear, you will just run it using somehow homomorphic encryption is nonsense again, right? I mean, you would need a data center that is 5 orders of magnitude in terms of storage bigger than what basically you have in your own computer to do that. That does not make sense. So these schemes, because of these limitations, are really restricted to doing a core computation that is simple, high value, and requires high degrees of secrecy. Okay? Now, simple computations that are linear are cheap, but as soon as you start having things that are nonlinear with a lot of multiplications, forget about it. This is not going to replace our current processors. Okay. Now, then there are some subtle attacks. So I said that the cloud is not trusted because they're only handling secrets. But look at this particular case here. So Bob encrypts a secret, gives it to the cloud to perform some homomorphic function. Alice encrypts another secret. But now the cloud is evil. Instead of the cloud actually performing the function that it should be performing, what it does is it just basically outputs the secret encryption that Bob gave it to be decrypted. Okay? So then the threshold decryption stage just proceeds as expected. And then what pops out here is instead of the result of the computation F, what pops out is actually the secret of Bob. So here we have an attack that leverages the fact that F is not high integrity, may actually be doing something different than what it is intended to do in terms of protocol steps that lead to a confidentiality failure. So again, no confidentiality without integrity. For many years, I remember actually when I started studying cryptography, we always had this kind of pseudo-neat idea that somehow we have confidentiality, we have integrity, we have availability. These three things are largely independent of each other. Look, we can have a scheme that offers only confidentiality. Look, we can have a scheme that offers only integrity. Well, that's nonsense. Modern cryptography has millions of examples where really, if you don't have integrity, your confidentiality suffers. And really the safe thing to do today, unless you're a genius and you can work things out from first principles, is everything has to have high integrity. And then on top of that, or within that, you do the confidentiality. So for example, here, this entity that is in the cloud should prove to the decryptors first that it performed the right function before they actually accept to decrypt. That's actually the solution to this problem. So clearly here there is more to it than just giving it to a cloud, letting it do its thing, and then decrypting anything that comes back. Because whatever comes back may actually not be what should be decrypted. So that's the first issue. The second issue is much more basic. Because the inputs are encrypted, how do you know that they're well formed? So for example, we discussed already the idea of voting for whether you prefer red or blue by encoding a 1 if you prefer one color and a 0 if you don't like it. But how do I know, if we run this thing here, that one of you is not going to be like, you know what, I really like blue. What I'm going to do is, I'm going to put 10 instead of 1 for my vote for blue. And then we'll add it up, and then we will have basically many more votes for blue than for red. And we're going to be like, well, someone cheated, but maybe you can actually put 10 there and something else somewhere else and fix it basically in such a way that it doesn't show. Okay? So this is a problem. And again, it is an integrity problem. Okay? We would like to make sure that Alice and Bob's inputs here are correct without learning what they are. And this is another big chapter in cryptography that is known as zero-knowledge proofs, namely proving things about secrets, such as that they are either a 0 or 1 and they sum to 1, etc., without actually finding out exactly what they are, that you need in order to make secure systems like this. Okay, so general lesson, don't even be tempted to think that you can have high confidentiality systems without at the same time making sure they have high integrity. You will open yourself to attacks such as the ones that we have discussed. Okay? Now, how do you actually prove that a system has high integrity here? That's a separate question. You can use these magic zero-knowledge proofs that I have mentioned. In fact, tomorrow in my credential talk, we will touch upon these for a little bit. Or you can just basically use replication. Instead of one entity basically doing the computation, you can have many of them, compare the ciphertext, compare different things in order to make sure that the computation was done correctly. Okay. Now, I promised to you that all the maths is over, so don't worry about it. We're not entering another chapter. However, I just want to give you an insight about the fact that homomorphic encryption is not the only way to actually do private computations. The second way that I just want to give you a hint of is secret sharing. So how does secret sharing work? So the main idea is that instead of each party encrypting their secret, what they do is they take the secret, they split it into chunks, and by chunks I mean they make a number of messages that all add up to the secret, and then distribute those shares, as we call them, to different entities. And the assumption here, the security assumption, is not a mathematical assumption anymore, okay, like the hardness of discrete logarithm, but instead, the assumption is that all of these entities that the secret has been shared amongst will not cooperate with each other to reveal that secret. Okay? That's the security assumption. It's a security assumption like the hardness of discrete log, except that it's more of a social assumption rather than a mathematical assumption. Any assumption is good for cryptographers. And then what happens is that these different entities now that all hold shares, I guess, of all the secrets in the room, have to cooperate with each other in order to cooperatively derive shares of additions and multiplications of the secrets. It turns out that addition is super simple. You take the shares of two secrets you have. If you want a share of the sum of the secrets, you just add them. No big deal. Multiplication, though, is slightly more complex, and it requires some precomputations before even the secrets are known, and some interaction between different parties. So every time you want to do a multiplication in a secret sharing scheme, you need to actually run a protocol amongst all of these people. That's the insight you need to have. So as a result, if you have mostly linear computations, you're good to go. You can do linear computations, just multiplications of constants with secrets and sums of secrets with no problem. As soon as you do multiplications, we need to interact, and then you're basically limited by your bandwidth across in the network. Okay. It turns out that secret sharing can also be augmented to have high integrity. And this is what SPEEDS is about. SPEEDS is a specific scheme by Nigel Smart and others in Bristol. And what SPEEDS does is, instead of just sharing the secret, you also secret share a MAC on the secret, a MAC like the one that Bart Purnell presented earlier, and then you do the computations in parallel both on the secrets and the MACs, and then at the end you check the MACs before revealing secrets to make sure that no one has cheated. So that's pretty cool. Very fast, very effective, and efficient. Just a picture in case, again, it's not really clear. So instead of X being encrypted and sent to someone and Y being encrypted, X is being shared. And of course, it doesn't have to be a peer-to-peer protocol, right? I mean, you can designate three people, like you three, okay, to be our authorities. And we all trust that you will not collaborate with each other to reveal secrets, okay? Maybe it's a bad assumption. Maybe I should pick 3 random people in the room rather than people who sit with each other, okay? So we split our secrets, we give a share to each of you, and now you, since you're close by and the network connections between you is good, you will collaborate to do additions, multiplications, until you actually have the result of the protocol here. And the nice thing about secret sharing, which is different from homomorphic encryption, is that when you are ready to reveal the result, it is actually the result in clear that comes out, not an encryption of the result. And this is simply because it is trivial to reconstruct the public result of the computation. You just publish all the shares, and you're done. Okay? So there is no threshold decryption. There is none of that. The results just come out after you're done computing the query. So pros and cons again. The pros are that the protocols are very well understood. It's very well understood how to do the sharing, how to do the addition, how to do the multiplication. There is no mystery about these things. Integrity, as I mentioned, comes for very cheap. You just double all your shares by also sharing message authentication codes, and everything works as before. And the actual operations are very cheap. Okay, so doing the addition is very cheap. Doing the multiplication in terms of CPU needed is very cheap. However, what is expensive is that to do multiplications, you need to do a protocol. You need to interact. Okay, and this is true as well for turning non-multiplicatively homomorphic schemes into fully homomorphic schemes. We could have taken the Ben-Allo scheme and actually run a protocol to do multiplication as well. So the two are actually quite similar, but these network interactions make very large computations impractical. In order to facilitate those multiplications, we need to do pre-computations, and that's expensive. And of course, there is the traditional problem of how inefficient it is to express big computations as circuits, executing circuits instead of executing on plain data, etc. So, and of course, the computation cannot be secret from the authorities. All the authorities will know what the computation is. So if you have, for example, the genomic testing example, it's not really clear. You can hide what the test does from at least those authorities. Okay. Now, overall, let's conclude. So I hope that many of you who came in the room thinking, okay, if I cannot see the data, it is self-evidently, clearly impossible to do computations using them, are now convinced, at least in principle, otherwise. Namely that, aha, maybe I can just be handling secrets and in fact do useful work without these secrets becoming revealed to me in their raw form. Okay? I hope that as a proof of existence, this worked in proving to you that it is possible. Secondly, I hope that you're convinced that in terms of the cost, okay, there are computations for which it would be practical, and there are computations for which it is doubtfully practical. I mean, so first of all, anything that is linear, namely anything that needs to take secrets, even a lot of secrets, just multiply them with constants and adding them. For example, polls, for example, billing, as I have described for smart meters. For example, doing statistics, okay, like getting averages and getting even variances if you encrypt x squared. Okay, all of these things can be done very efficiently. It's just multiplications of ciphertexts that are all there. Like there is nothing to it. So if your computation is mostly linear, and a lot of very high value statistics, as I said, and billing is linear, then you can just do it. You can do it today. If your computation starts having multiplications of secrets, lookups, whatever, you need to do full computations, then it really depends on what is the circuit depth that you need to express, and if it is too deep, then it becomes increasingly impractical. Okay, so don't rush to just throw away all your, all your servers in your basement and upload everything to the cloud, hoping that this will solve your confidentiality problem. It won't today. Okay, so the integrity is a big problem, and I hope again I have convinced you of this. However, we do have solutions to that. These solutions, though, add to the complexity of the schemes in terms of implementation and the cost as well. And then the final issue and the final conclusion is that all of that stuff that I have presented to you, even if you just kept an eye on the references, is very recent. So we understand how it works very well, but what I mean by we understand how it works is we understand the science. There is no much science left on how to multiply secrets or anything like that. However, the tool chains that you need to do proper engineering with this are just missing. They're not there. It was a little bit like, when people basically understood how to build compilers, but the computers they had were basically too small and the technology they had was too primitive to actually write proper parsers that could parse huge amounts of text, right? I mean, the theory of parsing was there way before we had good parsers, and it is the same here. The theory of how to do all this exists, but of course this cannot become engineering until we have tool chains, we have compilers, we have languages that allow you to express this and press a button that says play, like you do in Visual Studio. And then the whole thing just compiles into the circuit, gets uploaded into the cloud, the clients are all built, and then everything just happens for the programmer. If ever the programmers need to understand any of the stuff that you hopefully have understood, this will never happen, because there are at most 1,000 people in the world that I believe understand this stuff, and you're some of them now, actually, which is pretty cool. So I think that the big gap right now is bringing engineering, tooling, and all that stuff to make this more practical. Okay, I think we have a couple of minutes maybe for questions and comments. Yeah. No? Yes, please.
Are you involving some of full concept in some industrial applications to system to demonstrate these?
Yes, absolutely.
For example, smart grid, smart web products
Yes. So that's a very good point. So I have used these things for building real systems. So one application that I can send you more documentation about is in the space of smart grids and smart metering. And our collaborators from ENCS in the Netherlands, they are a center that takes care of industrial security and particularly smart grids, etc. They are working with Alliander, which is a DSO in the Netherlands, to do a field trial of using these techniques, the secret sharing techniques rather than the homomorphic encryption techniques, in order to gather statistics in smart grids. So the idea is that you have your smart meters in your town or something, and you want to find out the average consumption at a particular time in a neighborhood. The traditional way is a third-party way. You gather all the data, you do the statistic, you reveal the result, but then you hold all this quite sensitive, very time-granular data. Our protocols allow you to skip that middle step, so you basically get secret shares, and then you do basically the computation just on the secret shares and can get out the aggregates without having ever learned the very granular data. So just to give you a feel for also how long it takes to field these technologies, our initial trials were with just 4 meters, actually 3 and 1. One was the reference one, and the 3 were doing the aggregation to make sure we get the same result. And that took place maybe 4 years ago. Then a test bed of about 100 meters was built about a year and a half ago. And now they are basically standardizing. They're pushing it into a standardization track to have this kind of homomorphic protocols as part of the DLMS implementations. And I think they're planning now to have larger scale trials once it is standardized. Yeah. Or as part of the standardization. That's my understanding. Yes?
How hard are the integrity checks? You mentioned that
yeah.
quite complex, but is it?
So it depends.
Another
Yeah, so in the secret sharing case, if you use the speeds techniques, and this is why they're very cool, what you do is for every share that represents a secret that you hold as an authority, you also hold a share of a message authentication code, and that's it, basically. I mean, your storage is doubled, your computation is doubled, but that's that, basically. And then everything else you do, you have to make sure that the max and the shares keep in sync. And then what happens is before you actually reveal the result, what happens is that you check that the MAC and the share is correct of the result at this point. It should check at this point. And you do that check without revealing the secret. Then if the check succeeds, you're good to go and you reveal. Otherwise, you stop, someone has cheated. So it doesn't actually prevent cheating, but it prevents the integrity failure becoming a confidentiality failure, which is what you care about here. So that's for the world of speeds and secret sharing. Now, for the world of homomorphic encryption, it depends. What you need to do is for every operation, be it an input that has to be in a well-formed way or an intermediate computation that some third party does involving something, you need these parties to prove that the secrets they have in there are indeed of the correct format or that the computation they did is correct. So for the secret inputs, you can use zero-knowledge techniques to do that, and we will look at some of them tomorrow maybe. And that is kind of well understood, but we're talking about, so if the if the Ben Allo ciphertext is about 2 elements, then you add, depending on the complexity of what you try to prove, 3, 4 other elements as well. And this is just to prove, for example, that something, that you know what you're encrypting. Okay, like just knowing what you're encrypting, that is not just a random number. Now, if you need to prove something more complex, such as actually this is a ciphertext of one of these 100 things, then we start adding log n number of elements times a certain amount. So it can actually go more complex for more complex statements. And then, of course, the person performing the operation needs to prove that they did it correctly. So that can be done either by multiple people doing it without adding any randomness, or by, again, having zero-knowledge proofs. I prefer actually multiple people doing it to make sure that nothing weird happens. But then you can't have secret computations. Okay? And then the threshold decryption has to be done correctly, as well as the key generation has to be done correctly. And that is a couple of elements, and it's pretty fast to check every time. So that doesn't disrupt the message flow in any way. So just mere kind of, we did everything we were meant to do correctly isn't so bad. It multiplies maybe by 2 or 3 the amount you have to do and the type of computations you have to do. The proving complex inputs are correct, that's more difficult. That's what brings up the complexity. Yeah.
Thank you.
Yeah. Cool. It's a pleasure.